This glowing cyan line charts the volume of AI models released over the last few years, reaching a peak before shattering into three distinct directions. For professionals trying to integrate these tools into daily operations, this explosion of options has created total gridlock. Standard benchmarks like MMLU measure a model's ability to solve static logic riddles or recall trivia. While these scores look impressive on a bar chart, they fail to account for the variables of a real-world project, where context shifts, requirements evolve, and data is rarely clean. In these messy environments, a high score on an isolated logic test provides very little insight into how a model will actually perform. Foundational corporate philosophies dictate an AI's real-world behavior more than any generic intelligence score. Treating these tools like interchangeable calculators misinterprets modern AI architecture. To use them effectively, you have to look at what the engineers prioritized when they built the underlying code. OpenAI designed their ChatGPT model for absolute scale. Their engineering priority was broad accessibility, rapid feature deployment, and a massive external plugin ecosystem. They optimized for a high-velocity, general-purpose tool. Anthropic took a restrictive route with Claude. Their engineering prioritizes safety alignment, forcing the model to be deeply methodical, prioritizing transparent reasoning and strict contextual coherence. This maintains accuracy over very long documents. Look at this logic tree modeling these structural differences. If we map out these approaches, OpenAI forms a wide web optimized for reach, Anthropic forms a deep linear chain optimized for sustained focus, and Google's Gemini forms a third branch, explicitly engineered to fuse natively with workspace applications and process multiple data types simultaneously. If you watch the token routing through this architecture, you can see how these blueprints constrain the output. The ChatGPT web rapidly executes many small, disjointed packets of data. The Claude chain forces one continuous, scrutinized packet down a single path. The Gemini icons simultaneously absorb text, images, and raw data from the surrounding environment. These optimization strategies define the core logic of the system, governing how tokens are generated and how the final output is prioritized for the user. Drafting a 3-paragraph email is a solved problem. The actual professional constraint is long-form synthesis, maintaining narrative coherence, tracking complex arguments, and sustaining a specific tone across a 50-page technical report. Claude often leads in this category. Because Anthropic engineered the model to maintain attention across deep context windows, it holds the initial premise of a document in active memory, even after generating thousands of words of output. ChatGPT operates with a different cadence. Its high-velocity architecture favors shorter drafting. It pivots tone quickly and generates punchy output rapidly, making it effective for rapid content creation, though it can lose the central argumentative thread in massive documents. The alignment training that makes Claude cautious also makes it meticulous. That architectural bias towards safety translates into superior multi-page argument tracking for researchers and technical writers who require high logical consistency. Multi-step logical reasoning requires an AI to hold previous steps in memory while executing the next variable calculation. It is a fragile process where one incorrect variable can cascade into total failure. Claude manages this fragility by making its internal logic visible. It writes out its reasoning chain step by step. Because of its specific alignment training, it can catch its own logical errors mid-response and force a recalculation before outputting a final answer. Top-tier ChatGPT models match this raw logical capability, but they generally execute the process behind a black box. They resolve the logic internally and deliver the final answer, lacking the transparent self-correction mechanism built into Claude's default behavior. In an enterprise workflow, an answer you cannot audit is a liability. Transparent error correction provides a verifiable paper trail of the model's logic, which is more valuable for high-level operations than a black box response. Generating an isolated 10-line Python script to automate a spreadsheet is a trivial baseline. Professional software development requires maintaining variable continuity across a multi-file enterprise codebase. This diagram maps how Claude manages code. By representing a live software repository with these interconnected nodes, we can see how Claude uses its deep context optimization to hold the structure in active memory. It tracks variables across dozens of files simultaneously, without losing the architectural hierarchy. When the workload shifts to a localized debug, ChatGPT utilizes its plugin ecosystem. It isolates a specific file and rapidly executes discrete tools against it, diagnosing syntax errors and pushing immediate fixes with high velocity. Gemini bypasses both of these workflows for developers already operating inside Google Cloud infrastructure. Because it is native to the ecosystem, it can pull server logs and query databases directly from the workspace without needing external API bridges. Selecting a coding model relies on the immediate constraint. If the objective is managing architectural maintenance across a vast codebase, you need deep context. If the objective is rapid feature execution on a single script, you deploy the plugin ecosystem. Raw reasoning capability is secondary if the model cannot read your internal data. This barrier is called data friction, the operational delay required to manually extract, format, and upload private documents into an AI's context window. Google optimized Gemini to reduce this delay. By integrating directly into Google Workspace, it queries live Google Docs, parses Gmail threads, and pulls active search data from the backend. This enables multimodal fusion. Gemini can process a financial spreadsheet, scan a PDF invoice, and cross-reference an email thread simultaneously, all within the environment where the work is already happening. For heavily integrated enterprise teams, eliminating the manual export and upload cycle often yields a higher operational return than marginal gains in pure reasoning speed. Believing that a single AI tool can handle every professional constraint is an operational error. The standard for high-level execution is the fragmented AI stack. Power users deploy multiple systems simultaneously, routing specific tasks to the model architecturally built to solve them. Look at this matrix flowchart of a deployed stack. Complex architectural coding and heavy research synthesis are routed strictly down the orange pathway to Claude, relying on its deep context window. High-frequency tasks, rapid drafting, and specialized plugin queries are pushed down the green pathway to ChatGPT. Operations requiring deep querying of live company documents run through the blue Gemini pathway for immediate workspace integration. High-level professional utility comes from matching a specific task's constraints to the engineering bias of the model built to handle it. Audit your daily operations. Look closely at your workflow and isolate exactly where your time is being drained by complex logic tracking, data friction, or rapid drafting. Once you define your actual bottlenecks, test the tools empirically against those specific constraints. Ignore the generalized hype. Run your own data through the specific architectural pathways we mapped out and measure the results. While features will expand and model weights will shift, the foundational optimization targets remain the primary compass for how these systems evolve. Understanding those structural rules is the only reliable way to maintain a professional edge as this technology scales.